one is of particular interest to me since I'm a cyclist. Our next talk is efficient voltage regulator for electric bicycle. The team members, James Finley, Jason Fisher, Devin Kim, Kelly Welsh. The sponsor is a kind of an interesting little company in Belgium called Adagio. And again, one of our former students, Brian Tinsley, was their mentor. And Brian was in CSS, but he was my student when I was in the CSS department. So again, it's exciting for us to have our students now be involved with Capstone. And the advisor again was more. So thanks, Ron.
Good evening. Thanks for being here. Now, culminate what has been for us a year-long experience. We're going to share our experience, strengths, and hopes on what we did for this project and the obstacles we overcame to complete it. So we're going to be talking about our efficient voltage regulator as it pertains to an electric bicycle that runs a DC motor. Our presentation today is broken up into 4 parts, beginning with the introductions and motivation. The second part is going to be our hardware design. Then we'll have our results for testing that design. And then we'll cover our problems and the solutions we had to some of those problems. And then obviously the conclusion of the presentation. Our formal team organization is our project manager, James Finley, our facilitator, Devin Kim, our hardware designer, Kelly Welsh, hardware installer, myself, and our faculty advisor, Dr. Lincoln. All right, a little bit about the company we work for, Tigio, and the people there that we work with. We're starting with our chief scientist and project lead, Dr. Wolf Kahn, our industry sponsor, Brian Tinsley, and Adrian Henry, who is here in the back today. A little bit about the company of Tigio. They are a technology company that emphasizes products that serve a greater purpose in the world. Their software, their flagship software, X Patterns, is a perfect example of some of the products they did put out. And their implementation of this product at Berlin Orthopedics and Sports Medicine, Belgian Disc Law, encompasses what they're all about. Here's a few quotes here from some of the doctors there. So they want to make the world a better place through innovation. All right, introducing our electric bicycles. The idea of electric bicycles, it's not a new idea. It's been around for a while. But over the last few years, the demand for them as a use for transportation is growing quite a bit. A study by the Federal Highway Administration showed that between the years 2000 and 2011, 47% or trips taken by people grew by 47% in U.S. cities. And in the top 70 most populated cities, it grew by 73%. So that's the most people in the United States. So again, the idea of riding a bike to and from work or from A to B is becoming a more popular idea. And with the electric bicycle, it's going to open more doors to more demographics, people that didn't, thought, that wasn't a mode of transportation. It lets you go up hills, it makes it a little easier. So it's going to open doors for new groups. Mainly, we have 2 types of bikes. One electric bikes. One's on and off, and then the other type is pedal assist, and that's where our project kind of comes in. Tigio, well, we have a space on here, so sorry guys. Well, okay, technology has greatly increased the efficiency of batteries over the last several years, but the dynamic control of the systems that they power is just as crucial to maximizing a battery's available energy. So, Tigio's electric bicycle controller as a concept will be a prelude to other applications and into more complex systems than a bicycle. And by monitoring the inputs from the user and from the environment, Tigio hopes to drastically increase the distance a bicycle can go on a single charge. So now over to the hardware design. I'm going to hand this over to James Finley.
I'm James Finley. Now that we know the motivation for the project, let's go over the way Tigio approached the design. So using data analytics, they are going to take information from the system and like affect the motor through that data, but because it's a physical system, they need sensor data, and that means a hardware implementation, which is where we came at. They initially started with a simulation in MATLAB to simulate all the data that would be coming in and adjusting it, and what that would do to the motor to improve efficiency. And it's important to point out that this is just a proof of concept, so our final product is not something that would actually be for sale, but may eventually come to fruition. So the design request, SCGO approached us to integrate the hardware design into the bicycle so that they can use their algorithm that they generated from MATLAB to adjust the motor's efficiency and how much power is being delivered to the bike. Initially, our project was focused on the sensor integration for the bicycle, and the studio had already purchased some sensors, and so we tested them to make sure that they would work for the project. But we also searched for additional sensors, such as current sensors, that would work for the requirements that they had. However, the scope of the project changed, as sometimes it does, and we were told that we needed to create a way to have different voltages that they could switch between. And our primary focus shifted to that, as it was not a simple task to overcome. And it also needed to support the 60 volts and 10 amps that the bike would be at its max power level. And they also wanted a method for switching between the voltage levels very rapidly, upwards of 2,000 times a second. So our original design for the voltage controller was to use a voltage regulator. However, this has some faults that didn't quite work for us. It is not bidirectional, so it would work in adjusting the voltage to the motor, but wouldn't allow the voltage to come back on the phase line back to the battery. It also just uses resistors to drop the voltage down, so we're losing a lot of power simply through heat, and that kind of defeats the entire purpose of the project and attempting to increase the efficiency of the bicycle. So our next idea was to use the solid-state transformer, which is an idea that comes from the power industry that they're trying to use to change out the current transformers that they have by using transistors. They're able to use transistors to create a high frequency to go through the transformer, which allows for you to scale the transformer down to a much smaller level, which was a particular interest for us, because a larger transformer wouldn't be feasible to put on a bicycle. It also doesn't have resistors, so we're not just simply dropping the voltage across a resistor and losing a lot of power through heat. It also allows us to have current travel in both directions, so as the power is going to the motor and then back on another phase line to the battery. The way that it works is we take a DC voltage coming from the battery on that line, and then by alternating between the red and blue transistors, which ones are on, we're able to get an alternating current through the transformer. And then on the secondary side, we use the body diodes of the transistors to rectify the power on the outside. So we go back to DC when going to the motor. And then as the power comes back on the phase lines that are off, we use the transistors and alternate to go back through the transformer and then use these transistors to rectify before it goes back to the battery. And now I will hand it over to Kelly Welch to go over our results.
All right, this is Kelly Welch. So after doing all research on solid-state transformers, it's kind of hard to do research on them. They're pretty new, so reading a lot of thesis papers, but we finally figured out what we needed. We started ordering components, testing them individually, testing them together as a design. We had ran into some problems, had to do some more research, get some more components and test those. But after a while, we were able to complete this. This is our first working prototype. Here's the circuit. Our transformer's up here. It's the little motor we were running. It's obviously very messy. We use 3 power supplies, 2 functionaries, and an oscilloscope in running our circuit. Required a lot of wires and connections, which will obviously clean up quite a bit with our PCB. Here are 2 oscilloscope screenshots coming out of our transistors. So this is our simulated AC signal going into our transformer. This is with only the MOSFETs. It's not with the transformer or rest of the circuitry attached. Here on the right is the same signal, but going into the transformer now. As you can see, there's a lot of ripple on both sides. This ripple is caused from inductive spikes from the switching of the MOSFETs and the transformer itself. This rippling did not affect the functionality of our circuit, however, it did decrease our efficiency. We wanted to get rid of that. After getting the circuit working correctly, we then moved on to measuring the efficiency of our voltage regulator, essentially. Obviously, that's the important part. So we were trying to demonstrate a high efficiency regulator. To do so, we simply just calculated power with current and voltage. We just used the ammeter for the current, oscilloscope for the voltage, combining those 2. We did 2 different tests with 2 different transformers. The first was with our main transformer here, and then we did one with a smaller transformer. The smaller transformer did not meet our main power requirements, but it was good to use for comparison and efficiencies. We set both the transformers at a 2-to-1 ratio, so we're halving the voltage for our motor. For the first transformer, we achieved about 70% efficiency, which is lower than 75%. We were wanting to be higher than the voltage regulator. The smaller transformer, we achieved around 80%, which is a lot better, so we always need to focus on getting a high efficiency transformer to further increase our efficiencies. After that, I moved on. I used dip trace to create a PCB board. On the left here is the top layer. This is the same board for the bottom layer. As you see, there's lots of points on the board for future expansions, for testing, used by video later on. This is the completed board. We ordered just a bare bones PCB. It allowed us a really quick turnaround for a lot cheaper. It also gave us easy access to traces of other components. With 10 amps, we would require very large traces, about that size there, with 1 ounce copper. In order to avoid that, or custom ordering with bigger copper traces, we are just going to solder on top of these traces to increase their capabilities and their thickness, which made it cheap and a lot easier for testing. This board will be used further for development of this product by Tigio. And this area here that the blue arrow is pointing to is the unfinished portion of our board. This is where the voltage switching circuitry will go, which is now what Devin and Kim will be talking about.
Thanks, Keller. So my name is Devin Kim. I'm going to be discussing some of the design problems that we've had throughout this project. Our first and most significant problem was getting our voltage levels to switch. So as you can see here in this diagram on both screens, these little switches here represent the different taps of the transformer. And each one of these taps represents a different voltage level that we wanted to switch to. We originally approached this with assuming that we could use transistors, and we tried to just plug transistors into these different taps, and we soon found that this wasn't possible because the transistors didn't have a proper reference to ground. After that, we also figured that they can't switch AC because we also have to have current going in the reverse direction back to the battery. Our second approach was to use a triac circuit, or a component, sorry. A triac component, for those who don't know, is essentially a component that's a bidirectional diode that can go in both directions. And it has a control pin, which is kind of analogous to a gate of a transistor that you can turn on and off and control the direction of the current. These did meet our requirements for AC switching, but they were unable to operate at above 20 kilohertz. And we needed it to be at around 200 kilohertz, which is the switching speed of our transformer. This is something that the company will choose to do in the future for future Capstone team. Our second major problem was the MOSFET gate driver. So we ran into a lot of problems with this. We probably spent around a month trying to get this to work. At first, we just tried to plug in transistors into our circuit design that James had discussed, and we noticed that the transistors would just remain on. And we had no clue why. So after we did a lot of research, we found that the internal capacitance of the MOSFETs would build up, and called Miller capacitance, and it would cause the gate to remain on. And this was really a tough thing for us to get through. We actually destroyed around 30 or 40 gate drivers just in the process of trying to get it to work. We called an IR applications engineer, asking them how to use this, and they didn't have a lot of useful information, but they did point us in the direction of how to test this ICM. It wasn't until Dr. Winkler pointed out that we should look at the applications notes. And after we found this circuit that you see on board, we use this for our final design for our transistors. These are on every transistor that we're using. Our third problem was our inefficient transformers. So these transformers are, just to give you a little background, are custom made from China, custom made materials. They have relatively large power losses below 200 kilohertz, so we had to use 200 kilohertz in order for the system to work. We found the efficiency to be at around 85%, but we wanted to be more around 95% to be realistic for this project, because this is all about efficiency. For some future improvements for the next Capstone team, or for Otigio to continue on, would be a custom-made transformer. It has to be small in size, highly efficient. They're going to need better transistors, preferably with switching speeds less than 40 nanoseconds. Low R-on values to prevent the voltage drops of each of the transistors while they're on. And they're also going to need to figure out where to find higher frequency triads. These are really hard to come by. We looked all over online for these, and we were struggling to find them. In conclusion, this project has been a huge challenge for us. It's at the cutting edge of engineering, and it's truly an analog circuit design where there's a lot of Murphy's Law that comes into play. A lot of stuff will go wrong when you don't expect it. We essentially took a kilovolt level system and scaled it down to a 60 volt system. It was a lot of the losses came from like transistors and the transformers, and those are usually neglected at higher level voltages. Like 2 volts lost in a kilovolt is a drop in the ocean compared to 2 volts lost in a 30 volt system. So we definitely found that out the hard way. Some advice for future Capstone teams: order extra components. If you're doing analog circuit design, there's always going to be errors. You may even burn up some stuff. Don't rely completely on data sheets. They're a good guide. They have lots of specs and stuff like that, but use your own judgment, experiment. And if that doesn't work, then use application notes. Application notes have tons of useful circuits that will prevent you from reinventing the wheel. We'd like to give a special thanks to Dr. Wayne Caron for helping us with this design, Dr. Wolf Kahn, the Chief Scientist at Otigio, for providing this very difficult project, and Brian and Adrian for giving us a great collaboration and between the teams, and for ordering all of our components. And that concludes our presentation.
I have a question. How heavy would this be on the bicycle, and where would it be on the bicycle?
It's really light. There's really not much to it. It's just a PCB board. They ended up being about this large. It's probably less than a pound with all three of them, so it's not much difference in weight. With the current shape, it'd be kind of awkward on the bike, but you could put it between the top and bottom frames.
Okay.
The next portion of the bicycle, or just on the back behind the seat.
Do you think it could become a do-it-yourself kit that individuals could put on themselves and all that sort of thing?
Eventually, maybe, yeah.
Okay.
So you said you were bringing a kilovolt system down into lower voltage.
That's correct.
Where's the kilovolt portion come in? Is that portable portion of it, or?
That's because of the design that came from kind of the power industry, where they're kind of dropping down from like 100 kilovolts down to, say, 1 kilovolt or even just 500 volts in that range. And so we're trying to scale that down to something where we're only really just dropping it from 60 volts down to something like 30 or 15. So we get a lot more losses because the voltage drop requires the diode's consistent. So for them to lose 0.7 volts is really nothing, but for us it made a significant impact on efficiency.
Okay.
What's the reason for working at the 200 kilo?
That's the only frequency that this particular transformer has to operate in order to be efficient. It has to alternate at 200 kilohertz. Because we can't use DC, so we have to use an AC 200 kilohertz signal. It's just the specifications of the transformer. We aren't really sure why it has to be 200.
Right, too high.
Yeah.
You need a high frequency in order to have a small transformer to do it on a bike. The transformer in particular operated efficiently between 200 and 400 kilohertz. So you just use the lower end of that.
And planar transformers are just really difficult to get. They want, big 1,000 quantity purchases, and that one right there was a month lead time. So it was hard to get new ones in. We knew this pretty soon after we got them that they weren't going to be ideal.
Did you run simulations?
Unsuccessful.
Yeah.
We tried. When we simulated a multi-stem, we were at over 100 efficiency. So I was just in the wrong there.
Did the net spectrum mode? Any other questions? If not, I can.